Now we're going to talk about strength. And one of the important things in your machine design is you have an exact set of specifications and the machine is loaded as it's supposed to be and everything's happy. Then wah! Something comes out at you that you didn't expect. And like, for example, this loading of this car in this do-it-yourself parking lot. Notice there are 10 80-pound bags of cement in the back, or concrete. Now, was this just a hack, or were these people really expecting that they could carry all this home in their car? It's a good question. Strength, not to be confused with stiffness. You can have structures that are very, very stiff, for example, a glass tube, but break very easily. Both strength and stiffness comes from material that is placed far away from the neutral axis. Remember, back to topic 3, fundamental principles. And strength and stiffness in torsion both depend upon closing the section, right? Closed sections. A very key thing on strength as opposed to stiffness is when you have multiple loadings about different axes, how do you combine the effect of all these different loads into what is the way the structure is going to fail? And if you're doing the calculation by hand, you can take things apart for linear structures anyway and calculate, for example, the bending stress from this load, the other load about different axes, and then you can combine them using, for example, the Mises stress criteria. If you're doing finite element analysis, one of the nice things in the end is the check for your design, and even during some initial concepting, is combining loads, and then the program itself will do the combinatorial analysis of what's the effective equivalent strength or stress that your structure will see to see if it's strong enough. In either event, your first order analysis is a very powerful tool. For example, here is a section of a beam, a closed section beam, and there's a point load on it. And you ask, well, what does that point load do to? Why is that there? Well, for example, if I have a beam and I'm going to be really clever and design a structure like this, and maybe it's a really efficient structure, so the wall is very thin, so here's my neutral axis. So it's very stiff and strong globally. Here's my neutral axis. Because I've put my area, my mass, far away from the neutral axis. Fantastic. Now I've designed this machine, for example, a bridge-type machine. The long axis. And I've got some carriage that's running along the bridge-type machine back and forth. And I may have on here a bearing rail that I put on there. And here's the carriages, the shuttle that moves back and forth. Wonderful, brilliant design. Very efficient, very lightweight. Oh, so good. If I have high loads on this carriage, remember, imagine your whole structure is made of rubber. And I load it and watch what happens. That this structure can bend in, like shown here. So how would I do a first order estimate of what's happening? Now this is where finite element analysis is also very good as you're a designer and working in areas that you may not be familiar with and don't understand how to model. For example, this is taking this structure and in a finite element model, gradually increasing the length until you see we get to a point where to make it longer doesn't really do much with respect to predicting the deflection here or the strength. Huh, that's interesting. And I guess it actually starts about here. A little more accurate. I like that. So what is happening here? This is 1, 2, 3 erasers long. and 1 eraser tall. Hey, St. Benet's principle, baby. So when you have a large structure and you're looking at doing the analysis of it, you can sometimes say, oh, how do I do the analysis? It's got a point load, long beam, oh. You can start to guesstimate what's going to happen just by thinking in terms of St. Benet's principle, that the material far away from here really is not doing anything to support this. Indeed, if I wanted to estimate what is this point deflection, I wouldn't even take at 3 characteristic dimensions away is too much. I can take a section of 1 characteristic dimension, treat it as a beam that is simply supported, put a point force in it, and now get very, very close to what the actual deformation is going to be, this magnitude. So these are very, very powerful tools for your first order analysis, both for strength and for stiffness estimation, of taking the appropriate dimension slices out of a complex structure governed by St. Benet's principle, is how you proportion those slices when you pull them out. To do your local quick estimate, closed form of the strength or the stiffness, it allows you then to size things in terms of your wall thicknesses, your dimensions, complete the rest of the design of the structure, and then when you have the rest of the design structure, then you can do the finite element analysis on the complete machine to check the strength and stiffness of it. Now that's for concern of loading of 1. How do you design the machine for multiple loadings, for the hundreds of cycles, thousands of cycles, millions of cycles? Well, in a steel structure, the endurance limit is typically infinite if the applied stress is less than half of the yield stress. But you've got to be careful. It's not just the applied stress in terms of, well, I have the shaft and I'm putting bending loads on it. If there's a torsion load on it, it's the combined state of stress, for example, by von Mises criteria, that you have to use with respect to the combined set of stress has to be less than half of the yield. Where people get into trouble most often is with stress concentrations. These are the regions around holes or changes in dimension where the stress is amplified, as the stress is flowing through the structure. In order to change and get up to some other part of the structure, if the stress lines have to suddenly, the more suddenly they have to change direction, the higher the localized stress concentration can be. And it may seem counterintuitive, but often you have to remove material in order to make the localized stress lower. And by removing material, what you're doing is you're making the transition of the stress flow more gently. You don't want to make any sudden sharp changes. That's what causes owls. Now, when you're doing finite element analysis, you've got to be very careful that the mesher, either inherently inside of it, will do a very fine mesh, or you have to control with the parameters you can use the size of the mesh to give you accurate results. And one of the very important ways you can know how fine the mesh has to be, most finite element programs will allow you to, you just use the default, or you can tell it to go finer. And what I would do is, in a typical part of the structure I'm analyzing, let's say I have a shaft I've created. Applying a load, and I'm trying to investigate what size radius on this fillet do I need. And in the finite element program, typically you have a little slider scale that you can drag for the fineness of the mesh. What you would do is you would start with whatever the default is, and you would get what the maximum stress is. We'll call this mesh fineness. You get a value of, let's say, whoops, a value of, let's say, 1, at a mesh fineness of 1. And now I'm going to move over to make the mesh fine 2. And these aren't real numbers that mean anything, just that it's getting finer and finer mesh. And the stress goes to 1.2. And you'll keep making the mesh finer and finer until the stress stabilizes at some value. And what this is telling you that for this characteristic feature size, fine feature size, and this characteristic overall size of the machine part, this is the level of fineness of the mesh that's needed to accurately get a representation of what the stresses are around here. Okay? That would also be true, for example, when you go to have a hole. Your hole size may vary a little bit. And you say, well, why if I'm doing this fine meshness and I've got that hole, why do I bother to do this? Why not just start with a very fine mesh to start? Because it takes a lot more computation time, even in today's world of super fast, wonderful, marvelous computers. As you get the structure to be more and more complex, it can really start to drag down to do the analysis, particularly when you start wanting to play what-if analysis. And then you have to, once you do that level of fineness, and now I have, for example, this hole in this shaft, now you can start playing the game of, here's the hole in the shaft. Should this hole, if I do a cross-section, have a nice, gentle fillet on itself? Will that help lower the stress? On keyways, on shafts, are notorious for causing high stress concentrations. You know, keyways on shafts or holes in shafts. Remember, whenever you have a sudden change in something, it's often good to remove material and put in a nice gentle fillet to prevent that stress concentration. Okay? Now, let's go to remaining topics of how do we minimize the weight, maximizing stiffness and strength. And it'll be important as you're thinking about the design of things like trusses, what do you do about stress concentration potentials? You may have remembered this shape from before. We talked in topic 3 about the neutral axis theorem. And remember we talked about way back when how you can very, very quickly estimate the stiffness and the strength of this structure by calculating an effective moment of inertia using the neutral axis theorem. So you can read about it here in this part of the text to go back to topic 3. But let me give you this little hint. Remember, if I have a truss, these 4 chords, each of area A, and the truss is of some height h, how do I very quickly come up with what the moment of inertia is? Ah. Does that ring a bell? Good. Now you've got the detail, because that's what we're getting is finer and finer detail. How do I know how to put these braces? And should the braces be like this triangle, or this kind of triangle? Why are some this way and others are this way? Why sometimes do you see a post in the middle? Well, it gets back to the stability question of buckling. So remember, for initially laying out your estimate of the strength of the truss and the stiffness of the truss, you can use your estimate of the neutral axis, excuse me, of the moment of inertia based on the cross-sectional area. That lets you lay out your machine in terms of the size or depth of the truss. Now, when you go to design the details of the truss, you do the following. You know that for a simple beam, if I put a force on it, right, the stress in the beam equals FL, this is the moment, over I over c. This is the moment of inertia. This is the distance from the neutral axis to the farthest fiber. So c here equals h over 2. Okay? Damn, was it a h squared or was it a h squared over 2? Which one? I don't remember. Let's calculate it. You go ahead and do it without me. And let's see if we come up with the same answer. Okay, how many people came up with, using the neutral axis theorem, the distance from the neutral axis to the area is h over 2. There's 4 of these chord members. So I have 4 times the area of individual chord member times h squared, or h over 2 quantity squared, which becomes a squared h squared over 4. Because this 4 eats up 2 of those 2's. So see, it's over 4. Is that right? Maybe I'm wrong. You're supposed to check. Remember, peer review. But let's assume that's right to start. So we divide this by h over 2. This is c. And we get I over c equals a h over 2. Okay? That's supposed to be an h. So the stress equals FL2AH. I said, well, what's that got to do with the strength of the truss and where these ziggy-zaggies go? These are called the braces, by the way, the bracing. Well, remember in beam theory, this is the stress in the outermost fiber, and because the diameter of the cord is very small with respect to the depth of the truss, we now know that the force compressing this guy or putting that lower cord in tension, the force on the cord in compression equals the area of the cord times the stress. Huh. Okay, let's see what happens. The force in the cord equals the area of that cord member times the stress, which was the force times the length divided by the area times the height over 2. The force in the cord equals 2FL over H. In other words, the force pushing this member to compress it is independent of the actual area of it. All it depends upon is the depth of the truss. Now that is a really cool result. And it makes sense physically if you think about it also. That what matters is the depth of the beam, because that's giving you essentially the lever arm with respect to the lever arm that is being pushed on the beam. It's almost like you've got a very simple lever where this is the force that's being applied. So this is analogous to the length of the beam. And then the balancing force pulling or pushing on these chord members is analogous to the height of the truss. So that's a very important physical realization. How does that get to where these diagonal braces go? Well, now you get back into good old-fashioned column buckling. And remember this from topic 5 even. We talked about stability of columns or shafts. And that if I have a column and I push on it, how hard can I push before, bam, it buckles? And is this column in a truss, is it look like it's built in? In other words, actually that would, one end would be built in and the other end is guided. In other words, so the slope is kept 0 at both ends? Or does it look like it's literally simply supported? These represent little rollers, such that this motion is vertically downward. It won't buckle over sideways, but this is a no moment constraint, so the thing can come out like that. So if it was built in, the mode shape would be, which is much, much stiffer, almost an order of magnitude higher load capacity than something that is free to boop, just pop out. Since this is all very thin members, turns out that this is a little too conservative of a model. This is way too feeling lucky. So when I lay out a truss and put in calculating what the wavelength between diagonal supports are, I will use this simple, I would call this conservative model. And the reason it's conservative is it will predict the truss will fail at a much lower load than it actually will. Not much lower, but low enough so I have a little additional safety margin. So I get the depth of my truss from the requirements of stiffness and strength. I'm predicting the spacing or the pitch of my braces by a buckling criteria. The initial strength and stiffness, very fast, easy to do. And I don't even have to worry, as long as I can pick a truss height that will work, I'm not even going to worry about the bracing for the initial layout of the machine. When I go to the next level of detail on the layout design, that's when I'll do the calculation to determine what kind of bracing do I need. Now, why are the bracings always on the diagonal? Why do I not make a truss that looks like this? Oh, this is so much prettier. Why don't I do that? Why do I want to do because I say, well, I calculated this is the length that won't buckle. So why am I insisting on this shape? See, that's this, but I've added a diagonal, right? Well, it turns out that go ahead and build one of these, and you'll find that it really has no stiffness. You have to have the diagonal bracing in for the flow of forces to transfer. So what happens is you're having effectively a shear through the middle of this plane here, and it allows this structure to act as if it was an I-beam. You can model this using finite element analysis and this and compare the two. This you can also model just using this simple straight form, closed form we did. And compare the results. Run the little design experiment on your own using solid modeling, finite element analysis, and start to build an appreciation for your own internal instincts for how these structures deform. It's really important that you develop your own internal feel or experience. Now, from trusses, very similar type of analysis and thinking with respect to the neutral axis, stiffness, and in a composite, instead of having the bracing, which is those diagonal members, you'll have a solid, and it may just be foam, it may be honeycomb. In the case of plywood, you'll typically have a good layer of wood on the top and bottom and cheaper, softer wood in the inside. And you're not usually worried so much about the buckling of the top and bottom cord. The dominant failure mode when you're looking at these types of laminates is the shear in the middle. That you can't just put air in here because air has no stiffness. And like we just showed this type of structure, if it's just air in here, you get no stiffness. How did these guys get away with doing this? Why is this wing shape not braced diagonally? So this gets back to, you should never generalize because you might be wrong. If we added these on diagonals, it might be much stiffer. Do we need it to be that stiff? It might be much stronger, but do we need to be that strong? Versus, look how manufacturable this is, and you know what? I do have a triangle here anyway. Well, this triangle automatically, by default, end up supporting this rectangle where adding diagonals absolutely does nothing for me at all anyway, except add cost. So always question why and try to figure out what's going on. And it turns out when I first presented this and you think, yeah, why are they doing that? They can do that. That's okay. This is a product. They did it. And you look a little deeper and yeah, they already do have a triangle here for stiffness, for transmitting the shear strains. Now, the shear strain and hence shear stress in a beam of some cross-section, you can calculate by closed form. It's based on, if I have a beam and I put a load on it, you know, what is the shear force V at that cross-section? So at the base of the beam, the shear force, actually the shear is constant throughout a cantilever beam, with this shear force V is equal to the force. And it turns out that the shear stress is like a term VQ over I, where I is what we know as the second moment of the area. So that we get from the integral of area, y squared dA. And Q is the first moment of the area, or y dA. So it turns out in a beam, at the top surface, the shear is near 0. It has to be, it's a free surface. And the shear is maximum at the center. Now let's look at the units here. If V is units of newtons, and we said this is the first moment of area, this is going to be meters cubed, and this is going to be meters to the fourth, which would imply that the shear stress is newtons per meter. Isn't stress newtons per meter squared? What's missing? You go hunt this down. The key thing is that you can calculate what is happening in this plane. You can also calculate the shear at this level to determine the glue strength So this is starting to give you a hint of how do I define Q? Is it the first moment of this area, of this area? Okay, go look it up. So you use this the ability to calculate the shear stress in a laminate to make sure that if you have a soft core like foam, the soft core, which is nice and lightweight, itself doesn't just shear through the middle. And you also have to check the shear stress in the glue layers to make sure the glue won't let go. Very simple to do, very fast to do. And this should have piqued your interest in like, wow, I'd like to be able to design composites to really, really do good. And it turns out there's a spreadsheet that goes with the course too. You can always check. So now that we can calculate the shear stress in the neutral axis, which is very important if you're using, for example, a soft foam. And you can use, it's going to be a rigid foam, but it's foam, so it'll break suddenly. So this would be like the pink insulation foam you'll see often used to insulate. You can actually glue wood to either side of it and make a really stiff structure. Or you've got something like this beam we talked about earlier where we want to stiffen it up by applying plates in the regions between other members that are bolted to this modular stuff. And we want to apply plates to close this structure so it becomes a closed form structure so we get high torsional stiffness and will increase our bending stiffness also. And we talked about using an adhesive where you could adhere a plate, but then that's permanent. Maybe you want to be able to adhere a plate like a machine cover and make the system stiffer, but then be able to remove the cover very easily and service the inside of the machine. So we want the cover to be part of the stiffness and strength of the machine. So you can use something like a Velcro. You know, here are the hooks. Here's the fuzzy stuff. And I apply it. Now watch what happens. This has some compliance, but not very much. It's actually, in shear, it's quite strong. The little bit of compliance it does, remember this will stiffen this. It won't necessarily add to the static strength so much. It'll help a little bit, but it'll really stiffen it. And then I can remove it if I need to gain access later. In other words, the peel strength is much less than the shear strength for Velcro. And the reasoning is that when you're trying to shear it, you're acting upon the entire area at once. For peel, when you start to peel it, the compliance in this one structure allows you to start applying the stress at the very edge. And this is almost like a stress concentration issue. These guys are starting to let go up here. They're still attached down there. But as you pull more and more, you win. Okay, so remember that this is a very powerful trick when you're thinking about adding plates to structures to your machine, whether it's a cosmetic or a safety effect that you need to add coverings, that you can often get higher strength out of your machine for less cost and less weight by having the coverings or closures become part of the structure when they're closed. Hey, wait a minute. Isn't that what we showed a picture of with the car in the very beginning of this thing where the doors were all open? I don't want to be in my car when the doors are all open and someone smacks into me. But when the doors are closed, the structure becomes very stiff and wonderful to behold. All right? So, very, very powerful lesson from everyday things all around you. All right? And the simple solutions are often the best.